as if I had done something hard. So I had to fess up about that little story. Okay, you've had, by the way, I'm sorry, I have to in my classes I always have a rule that nobody can, can speak twice until I've gotten all the others. So, okay, Mark?
I wondered if you started with just a clean slate today, no baggage, no established program, how you would teach introductory computer programming.
How would I teach introductory computer programming if there was no history of the subject, and all this stuff going on? Yeah, wow, that's a great question. So let me see. So of course, I'm not sure my way would be the best, but what would I think would be good? So first of all, I would emphasize the hardware rather than the algebraic high-level language, and I would make sure everybody knew what was easy for a machine to do. Instead of because when you're programming in a language. Especially when you're a student, before you know that much about the way machines really work, you can't help but think that what's easy in the language is easy for the machine. So, for example, if I see people who were, pardon me, going to old languages, APL. If I see people who first programming with APL. They write programs like I would never in my wildest dreams write myself. The way to do something in APL is to take a problem and make it into a four-dimensional array, and then manipulate four-dimensional arrays and boil it down to one dimension and get your answer. But I know that a computer doesn't like four-dimensional arrays. So I would start by having people work with a RISC computer, a computer that has reduced instruction set. Four-dimensional arrays. So I would start by having people work with a RISC computer, a computer that has reduced instruction set but clean, and I would have them seeing the way caches work and the way paging works, and all the different things for speeding up pipelines and so on. But they would learn. They would learn something about the way machines go, at least for several weeks, to build their intuition. And I call this bottom-up teaching, computer science bottom-up rather than top-down. And I believe in any field, not just computer science, but chemistry, physics, whatever. People get to be, they get to the end of their careers, and they start saying, what would I teach differently if I could do it? And I think they make just the opposite mistake. Almost always you find that when you deal with abstract things rather than concrete things, the abstract things go farther, and you can make giant steps with abstract things, and working on concrete stuff you have to only go baby steps and small. So they'll say, okay, I've learned all these great abstract, like go baby steps and small. So they'll say, okay, I've learned all these great abstract ideas and high-level ideas. I'm not going to bother my students with the low-level ideas. They've already, that just takes longer, and I find that the high-level ideas are what really get a lot of mileage out of those. But they don't realize they came out okay, and they built their whole intuition. They could appreciate the high-level ideas because they had the structure to put them on. So they want to teach their students, they're going to build a house from the roof down, and it seems wrong. So my main answer is give the students a good idea as to what machines are like, and then they can learn higher level ways to simplify so that they can take larger and larger programs and put them on the machine. But that would be second. That would come after. Yeah.
Just wondering if you foresee the fundamental innovation in the area of architecture. We have seen a lot of innovation in programming and compiler theory and all these things. Do you see any fundamental innovation in computer architecture? Like since von Neumann, I think there is no fundamental innovation in architecture. No fundamental innovation in computer architecture.
What's the innovation in computer architecture?
Okay, so
Repeat the question.
the question is something like, is computer architecture sort of doomed to stay the same as it always has been for the last few years, or something like that. Anyway, I believe that we've come to some kind of an understanding of what efficient ways to do things, and some other things haven't worked. But there's one aspect that I believe is understudied, and it's what I call broad-word computing. And I have it in line 4A. I believe there's a good chance that that people could come up with a brand new style of computing that we don't know now. And I'll try to explain it in 2 minutes or something like this. Or something. So let me say, for example, we've got these big chips, memory chips, that have, let's say, n flip-flops in them, where n is very large, maybe 1 billion. Anyway, there's a large number of electronic components in these flip-flops, and the thing is, we call them flip-flops, but only log n of them are flipping or flopping. Most of them are staying in the same state. And that seems like a big chance for improvement, because because now we know how to build large arrays of these things. We might be able to think of some smart way in which all of them are changing a lot, like our brain does. So let's say, so I haven't worked out how to do it, but I know, for example, that you can build an adder that will add million bit numbers together, and the carry will go simultaneously. It doesn't have to go through stages of logic, but there are ways to add using the properties of physics that don't go into Boolean algebra into the data log the way people EEs have to specify their hardware now. These circuits are known, but nobody uses them. And so I found lots of programming tricks where we can use the properties of adding in combination with shifting by powers of 2 and by exclusive OR and logical other bitwise operations combined with these things, and we can do amazing things with these operations. And I have about 50 pages devoted to that in Volume 4. And I believe that this could lead to a brand new kind of architecture. But I don't have time to prove it. I just think that there's certainly lots of implicit power that's not being tapped when only a few of these things in our memory chips are actually changing state.